this way, which is the standard way of representing complex waveforms, you can also represent this way without any loss of information. And in fact, if you look on your phones and if you transmit images on the web, almost always they do a transformation something like this. So in the case of your iPhone, right, inside the phone, the music's being represented this way. But as soon as you pop it out to your earbuds, right, you need a wave to drive the diaphragm of the speakers. It transforms it back to this. So now if we have a higher frequency waveform, here's what it looks like in the waveform plot. Here's what it looks like in the spectral plot. If you want to vary amplitude, in this case, the waves have a higher amplitude than this does. I'm not going to even bother to play these sounds. So this would be a loud sound, this would be a soft sound, and that would be represented in the spectral plot, doing something like that. Now, here's where it gets interesting if you want to combine simple waves into a complex wave. You can do something like this. So let's say we take a simple tone like this one. Come on, cursor, show up. All right, low frequency tone. Here's a high frequency tone. All right, and now let's say we mix all those tones together to get a chord. And that sounds something like this. Okay, so we can have pure tones, high, low, or we can mix a bunch of other tones together to make a chord. Now, in the waveform plot, this can get arbitrarily complex. So if you mix these four things together, you end up with this. But in the spectrum plot, you just have 4 points in here. All right, so this is a very convenient way in signal analysis that people use all the time. Now, you folks aren't in here to study signal analysis. You could care less. The reason I'm showing you this is because there's an overwhelming amount of evidence to suggest that this is what the visual system is doing as it goes from the retina to the primary area of the visual cortex. And so that's what I want to do today, is to develop that in the first half of the lecture, and then in the second half talk about some of the consequences of that involved in the history of art, and I'll show you a whole bunch of really cool paintings by Salvador Dali that exploit this basic principle. Okay, so here we're doing it in sounds, and this is where the Fourier analysis actually came into place. It's sort of natural to think of sounds as varying in frequency, and researchers were doing that all the way back in the 19th century, and they were explaining the function of the ear using this way back in the 19th century. But it was much more recently than people said, well, you know, you can do the same thing in vision. All right, so in this case, right, we have a wave that looks like this. You can think of these instead of intensity variations in sound, right? These are intensity variations in the brightness of a pattern. And so these are four simple sine waves, luminance patterns. These things, by the way, are called gratings. I have no idea where that term comes from, but a sine wave modulation of brightness is referred to as a sine wave grating. And here's what it looks like if you plot it in a waveform plot. And here's what it looks like if you mix these guys together. And so in a spectral plot, it would look like something like this. So here's the basic idea. If I go from a waveform plot to a spectral plot, this is what's referred to as Fourier analysis. I know we have a bunch of engineers in this class. How many of you have done this before? See, a few hands have gone up. If we go the other way, That's called Fourier Synthesis. All right, so if you take a good analog of this, if you take a photograph with your camera and then you store it in, say, a PNG or TIFF format, you're doing something like this. When you then play that back as an actual image, or sounds work even better. So if you go from, what's the best, MP3s, right? So if you record your sound as an MP3, you're doing this process, but then when you play it back, you need it in this format to actually drive the speakers. You're doing Fourier synthesis. And I'm going to argue that the brain does the same thing. Now, we're not doing audition in this course, but the brain does this both for audition and for vision. Yeah?
If you record a sound and store it on, like, in analog, so on a vinyl or something, is it not doing a...
It's in the waveform.
Okay, the whole time.
It's in the waveform. So basically, it's just a groove where the needle goes up and down. Record in vinyl. Are you guys old enough to remember vinyl?
It came back.
I've seen the price of some of those things. I went down to my basement the other day, and I have, like 2 whole shelves of vinyl records. Of course, when I read the prices, they were, you get $5,000 for this record if it's in mint condition. I assure you mine are not that way. But all right, now typically when we do this in Vision, we can do it in a different way. We can use what's called a wavelet analysis. I won't be testing on you. I'm just telling you basically what it's like. So it's a set of filters by which you filter an image. And the typical building blocks look something like this. So you sum the filter multiplied against the input. And so you have an excitatory part in the center flanked by 2 inhibitory parts that looks just like the behavior of simple cells in the striate cortex. All right, so the way the telephone engineers transmit images over when you do your streaming TV, they're encoding it in much the same way as the brain is encoding visual information. All right, so let me get you through some terminology here, and I'll try and convince you that this really is what the brain is doing. So a stimulus like this, I told you before, is referred to as a grating. And we can have square wave gratings that look like this, or sine wave gratings that look like this. This is one cycle of the grating that you see here. And so you can have abrupt changes or you can have smooth changes. Most research in the field uses these. Now, the way we measure the width of gratings, you don't just put a ruler on top of the image. We express it in terms of visual angle. So that means if you take the same grating at a long distance, the cycles are shorter than if you see it at a short distance. And to just give you a hint, if you hold your thumb out at arm's length, the width of your thumb is about 2 degrees of visual angle. All right, you bring it closer, it's maybe 1 degree of visual, or maybe 4 degrees of visual angle. Farther away, it would be smaller. So typically you can see it down here. So here we have, this eye is looking at this young girl from this distance, and this is the visual angle of the girl. If she moves to a farther distance, the visual angle is smaller. All right? So, rule to remember. Small things, small visual angles. Big things, large visual angles. Now it gets a little confusing if you do both vision and audition because we typically don't talk about frequency so much when we do visual stuff, and frequency is the opposite of the wavelength. I'm sorry, not the opposite, the reciprocal. All right, so what can you do with a grading? Well, one of the things you can do is you can vary the frequency. So notice here, we have 2 cycles in this square patch. So this is referred to as a low spatial frequency grading. Here we have 1, 2, 3, 4, 5, 6, 7, 8. This would be a high spatial frequency grading. So gratings can vary in terms of their spatial frequency. They can also vary in terms of their orientation. So in this case, their changes occurring horizontally. In this case, it's occurring diagonally. And then finally, they can also vary in terms of their contrast. If you have a stereo at home, if you have an amplifier and it measures the power, root mean square power, that's a measure of contrast. So you're looking at how big is the range relative to the mean. And so this would be a very low contrast grading. The range is pretty small. Here it's a little bigger, here it's higher still. So this is high contrast, medium contrast, low contrast. Right? So given grading, we can vary the spatial frequency, we can vary the orientation, and we can vary the contrast. And again, just to redefine contrast, typically we define it as the amplitude divided by the mean. And so if you did it in a waveform plot, this is what the 3 different contrasts would look like. All right, now this is an interesting diagram because what it does is it varies spatial frequency along one axis and varies contrast along the other. So who haven't I picked on a while? Let's pick on you. Tell me what you see here.
It looks like it's moving away from you. The grading is kind of
All right, well, let me try to nail you down a bit. Do the heights of the regions where you can see the gradings the same? Right, so is the highest part where you see any variation around here?
Yeah.
And is the lowest point down here and same down here? It sort of runs out of gas somewhere near here. All right, what this is showing is that our sensitivity to contrast varies as a function of spatial frequency. So there's one spatial frequency that we're much more sensitive to than we are to others. So even if you measure, well, the main point here is there are a lot of spatial frequency, there's a lot of information that's coming into our eyes that we can't see. Either the frequencies are too high or they're too low or the contrasts are too low. Now, if you're an engineer and you're trying to do data compression, what might you want to do? All right, engineers in the class, raise your hand. Nobody wants to admit it now. All right, I won't pick on you. If I'm trying to compress the data as much as I possibly can, and I know that some parts of the data humans can see and some parts of the data humans can't see, what would be a useful strategy to compressing the data?
Cut out the stuff we can't see.
Throw away the stuff you can't see, nobody cares, because they can't see it. All right, so that's one of the uses of this kind of Fourier analysis and vision research. It also provides a tool that we can study various aspects of the visual signal that I'll get to in a second. So if we look at, it also provides a tool to look at different species, which I'll also talk about. So here we have the stripes that are visible and the stripes that are invisible. And you get this curve that looks like this. And this is sometimes referred to as the contrast sensitivity function. And this varies for different people. So if you have really high acuity vision, right? So if you take young people like yourselves, you'll have a contrast sensitivity function that looks like this. If you do this for me, you might get one that shuts off much earlier as my vision is deteriorated from old age. It is corrected though, so with correction, it would probably be about the same as yours. Now we can use this to study your visual function in different contexts. So here, we're in bright daylight. This is what's sometimes called photopic vision. You get the normal contrast sensitivity function I showed you. If you look at vision at night, where your rods are dominating, you get a contrast sensitivity function that looks like this, right? So your vision at night is much less than your vision in bright daylight. And the contrast sensitivity function is one way of documenting that. And then in the evening, it's somewhere in between. Similarly, I gotta change this slide. I've been doing this for 5 years. Every year I say I'm gonna change the slide, and every year I forget. Last time I heard infants were humans. So if you look at the adult contrast sensitivity function, you get something like this. But when you're first born, a lot of your visual system hasn't developed yet. And you get a contrast sensitivity function that is much reduced relative to the adult. So pretend this as adult and not human. Similarly, if you look at old age, I'm guessing most, yeah?
For the first slide of these, does it matter if what you're looking at is black and white or color?
Yes, it does. And I don't want to go into the details of that. Color makes things, color's a whole nother thing. So let me avoid, we'll do color vision a little bit later in the course. Or actually, will I do color vision? No, I don't do color vision in this course. It's a good question, and I'm choosing not to answer it. If we look at people of different ages, right? So 20-year-olds, like I suspect most of you are, you know, you're at your peak visual power. Now, I'm not this old yet, but as you get older, it sort of drops off the contrast sensitivity function. You can also use it to study animals. I think this is where the human label came from. I substituted one curve where I should have changed the name on it. So if you look at humans and rhesus monkeys, they're pretty much the same. If you look at cats, for example, they're much better at seeing low spatial frequencies than humans are, not so good at seeing high spatial frequencies. Dogs are the same. So my dog Macy, when she loves to sit in the front of the house and bark at anybody who walks down the street, even if it's somebody she knows. However, because her vision isn't as good as ours, she doesn't know that she doesn't know the person unless they get sufficiently close. So she'll bark at everybody unless they walk up to her, and then she starts wiggling her butt and wagging her tail and saying, "Come pet me, come pet me." They have goldfish, pigeons, you know, it's all over the place. So this is one way, using this technique, that you can compare the visual systems in different animals. So now let me go back to the last lecture. So I've explained to you, hopefully, a little bit about the Fourier encoding of stimuli. And we talked about the contrast sensitivity function. Now let me remind you a little bit about what we said last week before I went off for Europe. So neurons in the visual cortex are tuned to particular features of a stimulus, bars of a particular width and orientation at a specific position along the retina. At higher levels of processing, these features become more and more complex, and the functions they are involved with become more and more specialized. So this is the orientation tuning curve of a simple cortical neuron in relation to the orientation of a bar or grating stimulus to the firing rate of a cell. Note the cell represented below responds over a 40-degree range of orientations. So the idea here, you're recording from a cell and you show it that grating, all right? And the cell says, oh, I like that. I'm going to fire at a high rate of action potentials, right? So you show it this, and if you're listening to the action potentials in an amplifier, the cell's going, it's firing away like crazy. All right, now if I tilt the grating a little bit, the cell might go at a much slower rate. So if you look at the rate of action potentials as a function of orientation, you see for this particular cell, it peaks when the orientation is vertical, and as you rotate it in either direction, either to the left or to the right, the cycles per second drops off until about 40 degrees, it's not influencing the cell's behavior at all. So this is what we saw by looking at just doing direct recording from the visual cortex. All right, now let's think of this now from a more engineering perspective, as if what the cell is really doing is coding spatial frequency and orientation. So this is the frequency tuning of a simple cortical neuron, and you see different cells have different optimal spatial frequencies. So this shows the orientation tuning, and this shows the tuning to spatial frequency. So this one likes high spatial frequencies, this one likes low spatial frequencies, this likes spatial frequencies in the middle. All right, so how can we explain that? This is what a receptive field looks like of a cortical simple cell. All right, we got a vertical band, which is excitatory. So if you shine a light in here, the cell's rate of action potentials will go up. If you shine a light in the peripheral regions, it will go down. So now let's put some grating stimuli on top of this receptive field. What's the cell going to do to this grating? Back corner.
Would it turn on?
A lot or little?
Little.
Why do you say little?
I'm not sure.
The excitatory region is completely filled with white,
Yes, all the way.
and the inhibitory region is completely filled with black. So this is the most optimal stimulus for this cell. There's nothing you can do that's going to make the cell fire more than this. It's like the Goldilocks issue, right? This bed is too hard, this bed is too soft, this bed is just right. So for this particular cell, this grading is just right. Yeah, you had a question.
So would this be a on-center cell then? Like an on-center receptive cell, since it's...
Yeah, this is an on-center receptive field, so where it has a plus, any light in this region excites the cell. Any light in the flanking regions inhibits the cell. And so the optimal stimulus is one where all the light is in this region and none of the light is in this region. Okay? So let's consider another possibility. Let's pick on you again. How's the cell going to respond to this stimulus?
Not as good as the inhibitory is in the middle.
Right, so it's getting excitation from this region, but it's also getting inhibition from here, and those two cancel each other out. So the cell, if stimulated with this low spatial frequency, is going to respond at its background rate. So this is the bed that's too soft. And now let's consider this one. Let's pick on you this time.
Me?
Yeah, you. That's what you get for sitting in the front row. All right? How's the cell going to respond to this?
It will be somewhat excited, but also inhibited, because there's some light in the center, but then also some light in the inhibition too.
That's the right answer. See, it's good to get picked on. All right? So here it's too hard. Here it's too soft. And here it's just right. So the idea is that these cells, they're not really responding to bars. They're responding to the whole pattern. All right? And so these cells are specifically tuned to particular spatial frequency. So this cell loves this spatial frequency, doesn't much care for that one, and doesn't much care for that one. Right? The cells are tuned specifically to spatial frequency. Yes?
I'm having a hard time putting this into like math is not like black and white stripes. So, what do they really respond to like in real life?
All right, you ask a very good question. I'm glad you ask it because I probably went over this too quickly. So what that Fourier theorem says is you can take anything, any picture you can imagine, and code it with a set of filters that look like this, right? So imagine you have a bank of filters and they have all possible spatial frequencies and all possible orientations. And I take an image and I run it through that bank of filters. What the Fourier theorem says is that all the information that's in the image is captured by those different gratings at different orientations and different spatial frequencies. So if you wanted to do a Fourier synthesis and try and get it back, you could do it mathematically. That's the trick. All right, now I really don't want to go into the details of the mathematics by which you do that. It's truly ugly. I used to do a lecture on the hierarchy of scary symbols in math, and one of the scariest is I. How many of you know what I is?
Like the imaginary number?
It's an imaginary number, right? So this gets you deep into I's, and want to avoid that. It's really hard to imagine imaginary numbers. But again, I want you just to get it conceptually. The idea is you're guaranteed if you code a stimulus this way, you can extract all the information in a way that you can get it back later if you want to and turn it back into the original image. All right, so when you look at a ping file on your computer and you call it up into Photoshop, that's what it's doing. It's taking that encoded image and turning it to something that you can understand. Does that help?
Yes.
Yeah, you had a question.
So when you were talking about your dog and how he or she responds to high frequency or low frequency more?
You mean my dog?
Yeah.
Her high frequency is less good than my high frequency.
So does that
In vision. In audition, we're not even close. Her high frequency is much, much higher than mine.
So does that mean that someone who is far away, that's low spatial frequency, like in the visual field?
Let me come back to that question, but you're on to a good topic. So what that means is, so what happens when you get farther away?
It's smaller.
The high spatial frequencies get smaller, right? And they might get below the threshold that you can see, right? So when you're looking at stuff far away, a lot of the high frequency content in that image you can't see anymore. But the low frequency content you just might see. Keep that in your mind because we're coming back. I'll show you a painting that if you look at it far away, it looks like one thing, and if you look at it close, it looks like something else. Any other questions before I move on here? Now, I realize this stuff is a little bit alien to you. I don't expect you to understand it at a deep mathematical level, but I'm hoping that you can get it at a conceptual level. And I'm really hoping that when I show you some examples of this in actual real paintings, that hopefully it'll make a little bit more sense. All right, now just to give you a sense that we have these channels, let's do an experiment. And what I want you to do is just stare at this rectangle right here. All right, and I want you to stare at that rectangle for, well, let's say a whole minute. So what's happening while you're staring at that rectangle? Well, you've got neurons that are responding to those spatial frequencies that are becoming fatigued. And that's going to affect their output. So let's keep staring at that rectangle. And your poor neurons are going, stop this, I'm getting tired. I can't stand looking at those gratings much longer. All right, now I'm going to switch to another slide. Keep staring at that rectangle. I'm going to switch to another slide, and I want you to tell me which bars look narrower, the ones above the rectangle or the ones below the rectangle, okay? So if the narrow ones look above, holler above. If the narrow ones look below, holler below. But now if you look at them, they're both the same, right? All right, so what I did was, here, I'm adapting the cells that are sensitive to low spatial frequencies, which makes that sort of degrades the output of that. Here we're degrading the high, and that causes an after effect that makes these look high and these look low. All right? So let's break down how that works. First of all, I'll tell you how we measure the responses to the individual gradings. Now, none of you are psych majors, so you don't have to perform an oh, you are, but you've already taken Psych 100, right? I tell students in my introduction class that if they see an experiment on adaptation to gradings, run to the next state. This has got to be the most boring experiment that a human can participate in. And as a result of that, they wouldn't dream of using students in an experiment like this. You use your graduate students who are slaves. Or yourself, just to show that you're tough and can take it like the... so here's the deal. You measure contrast sensitivity as a function of spatial frequency. You adapt the observer to a high contrast grading of fixed spatial frequency. You remeasure the contrast sensitivity as a function of spatial frequency, and then subtract the second measure from the first. Now, it's this adaptation, right, where you have to stare at these things for like a minute or 2 minutes to get the adaptation. And then you get one data point from that, where you test the threshold before and after, and then you have to do the whole thing again. You have to let the system normalize, then adapt again. So an experiment like this could take forever. But here's what it looks like. So let's say you measure contrast sensitivity, like so, before any adaptation. And you get the curve with the solid black circles. All right? Then we adapt the subject, in this case, to a spatial frequency around 8 cycles per degree. And then we remeasure the contrast sensitivity function, and you get something that looks like this. So what this is showing is by adapting to 8 cycles per degree, your sensitivity to that goes down a little bit from what it would be like in the unadapted state. If you subtract those two curves, you get something that looks like this, which looks just like the spatial sensitivity of actual neurons in the cortex. So for example, if we, here are the results from adaptation reveal that you've got several bands of spatial frequency sensitivity. So this is from neural recordings, and this is from adaptation studies. All right, so the idea here is that you can measure the tuning of cortical neurons without having to stick electrodes inside your brain. Right? So if I want to measure cortical tuning in you, you're probably not going to let me open up your skull and shove electrodes in there. All right? You probably don't want me to do this adaptation procedure either, but it's much better than opening up your skull. I mean, even graduate school students would balk at that. How many graduate students we have in here? You'd all balk at opening up your skull for the professors. But you might submit to an adaptation procedure. So now one of the questions is, how do we get high precision to spatial frequency if we've just got a few channels? You have a similar thing in color, right? I mean, we can see an enormous amount of colors, but we only have 3 color mechanisms. And so people have asked, how do you get very precise color discrimination with just a small number of channels? And the way that the brain does this, in all kinds of domains, is that it looks at the relative activity of different channels. So let's say we look here. So suppose I've got 3 channels of neurons. This is to orientation. So this channel likes gratings with an orientation of 30 degrees. And if you look at its activity, it's maximum at 30, hardly at all at 60. The red channel loves 60, doesn't much like 30. And the green channel responds an intermediate amount to both 30 and 60. And so the way that you get much more precision out of this system is you look at the proportion of activity in each channel. All right? So if you're getting, say, lots out of the 30-degree channel, none out of the 60, that's telling you you're looking at a 30-degree orientation. And similarly here. So it's the combination of all 3 of these that's what's specifying orientation. So this is what a 30-degree stimulus would look like. You get a lot of activity in the first channel, moderate in the second, hardly any in the third. For 60, that flips. All right, so let's see how we can use this to explain the adaptation study. So before adaptation, let's say I have cells that respond a lot to medium width bars. I've got a smaller number that respond to narrow widths and a smaller number that respond to wide widths. All right, now let's say that I adapt to wide widths. What's that going to do? Well, that means that this channel gets fatigued and the output will lower the activity in that channel, and therefore you'll mistakenly believe that the bars are narrower than they really are. Similarly, if we adapt to the narrow bars, then the narrow channel will be suppressed, and you'll think that the bars are wider than they really are. That's the idea. That's how adaptation works. I'll show you another example. This one probably isn't going to work with everybody, but let's give it a try, Mike. So what I want you to do is to stare at this red dot. And let's let this one go for a minute and a half. All right, now when it stops, you're going to see another grating. And I want you to tell me whether the upper ends, so this one looks like the upper part is shifted to the right, right? All right, now what I want to do is once I stop the adaptation, I want you to tell me whether the grating that you see looks like the upper part is oriented to the right or oriented to the left. Let's just stare at that dot. You are getting sleepy. Not as sleepy as I am after 14 hours of travel. Stare at the dot. Let's go another 30 seconds. All right, now when I switch the slides, I want you to holler out left or right, whether the upper part is shifted to the right or whether the upper part is shifted to the left. Okay, 1, 2, 3.
Left.
All right, that's the orientation after effect. All right, exactly the same as spatial frequency, exactly the same explanation. Using the orientation channels in this case rather than frequency channels. And I'm not going to go through this sort of convoluted explanation of all that. You can look through this slide on your own, but basically it's the same story as here. All right, so once you adapt to them, rotate it this way, the channels sensitive to that get adapted, and then when you look at a vertical one, you get an adaptation that shifts it in the opposite direction. All right, so this is the procedure is exactly the same as before. You measure contrast sensitivity as a function of orientation, adapt observers to high contrast grading of a fixed orientation, remeasure contrast sensitivity as a function of grading orientation, subtract the second measure from the first. And that's how you measure the orientation tuning curve in an intact human without having to go in and stick an electrode in the visual cortex. So this is what you would measure in terms of neural impulses per second. So this is neurophysiological data, and this is data on the same animal using that adaptation procedure. Yeah?
So do like neurons for the same for different orientations like at the same rate? Like it's like a vertical orientation grading and then like a horizontal orientation grading? You showed those, like,
Yeah,
two
so the
images.
neuron experiment is easier, right? So I'm recording from a neuron, and then I show you a grading looks like that, and I measure the spike rate, and then I take it away, let the animal rest, and I show you this, and measure the spike rate, and I show you this, and measure the spike rate, and all things in between. And so you get a function, which is how the spike rate varies as a function of the orientation of the grading. And so for this particular neuron, it prefers vertical gradings and then drops off like so as you systematically vary the orientation. All right? Now, if we do the same thing using the adaptation procedure, lo and behold, we get a curve that looks pretty much identical to the one that they have over here, suggesting that we're measuring the same thing. We're just doing it in a different way. Any other questions about this particular procedure? Okay, now having done this, I have to confess, this area called spatial vision is probably one of the most boring possible areas of visual perception. Used to, when I started doing this class, I did a couple of lectures on it, and I gradually have squeezed it down to a half lecture. Again, the point here is to get the gist. There are two things I want you to get from this. One is that we can measure behaviorally the same thing that we can measure neurophysiologically. But the more important principle is what this suggests is that it looks like in the early cortex, the brain is doing something very much like Fourier analysis, which makes sense because we know from a variety of analyses that this is probably the most optimal coding that is mathematically possible, right? So the brain has adopted a strategy that really is optimized for making the data as compact as it possibly can. So let's try to turn it into real life, and I'll come back to your question and say, well, how do we apply this to individual images? In order to do that, I want to tell you about one of my favorite painters. I assume you've all heard of Salvador Dali. Have any of you been to the Salvador Dali Museum in St. Petersburg? You have?
Yeah.
Is it awesome? Okay, so Dali painted between 1904 and 1989. He sort of became a parody of himself in the 60s and 70s. But he's the guy, or one of the painters that brought us surrealism. Very interesting, weird guy. Now, one of the things that Dali did is he had a series back in the 20s where he would paint what he called double images. In fact, this was a theme throughout his career. And he did the double images in a couple of ways, and I'll talk about some today, and I'll talk about some next time, that are double images for different reasons. So let's consider this image right here, and I'm picking on you because you're in the front row And you got to tell me what you see here.
I see people. I see a woman at a table. Looks like people wearing like a robe, like apron type things, black and white, and it looks like 2 hallways.
Okay. Let's take you in the back room. What do you see?
A man's face in the middle.
So those people that she said were dressed in black and white robes, you see a man's face? You think that's a little weird?
I mean, I don't see it.
She's not going to challenge your perception. Can you give me an explanation of why you see something different than she does?
Because of the way our eyes are able to focus with the distance in between.
Right. So far away, the low spatial frequency, the high spatial frequency is filtered away. You can't see it. You can only see the low frequencies. But she can see the high frequencies. So the high frequencies, right? This is a head, this is a head, this is a head, this is a head, right? That's what you're seeing?
Yeah.
What she's seeing in the back is this is a head, that's a nose. And in fact, if she were very erudite, she might recognize this as the bust of Voltaire, which you see in the title. All right?
Crazy.
Now, you may think this is weird. I can make you see it.
I'd have to go.
And all I have to do is blur the image.
Oh, I see it now.
Now you see the guy?
That's scary.
All right, so what Dali's doing here is he's painting 2 different scenes. One at a high spatial frequency, one at a low spatial frequency. Your brain is coding those pretty much independently. All right, now at close distances, the high frequency is going to dominate. That's what you're going to see. But if you blur it, or if you look at it farther away, then you see the bust of Voltaire. And that's where he gets the slave market with the disappearing bust of Voltaire. So he's doing this stuff in the 1940s. And he did a lot of them. Here's another example. We'll pick you in the front. What do you see?
I see like a face there and a face, 3 faces, I guess. One
Yeah.
in the middle and one on the left and one on the right.
Yeah, so here he doesn't mask the face, but you can also see this drooped over lady
Really?
with a hood on her head there,
Oh, I see. Yeah.
right? And in this case, you see a nurse with her,
Oh, okay. I
Sun?
see, yeah.
all right? That's the high spatial frequency. Now, those of you in back just see the face, and the face. So this is old age, adolescence, and infancy. If you blur it, the faces become much more clear. Now, for this particular one, he did a study to get there. This has, I think, one of the greatest titles of a painting. Oops, going the wrong way. Mysterious mouth appearing in the back of my nurse. Right there. So if you blur it, this becomes the face, and that's the mouse, the mouth. And then the buildings in the caves back here are the eyes, and this is the nose. Again, it doesn't hang together all that well in the original, but if you blur it, you get that. All right, now notice the dates on these things. So the first one is 1940, second one is 1940, third one's 1941. So Dali's painting these things in the 1940s. And then he stops, says, all right, I've done this, I'm bored. Until in the 1970s, he paints this thing. So front row, what do you see?
Oh, back of a woman.
And what's she doing? She's staring out, looking at the,
Looking out the window on this side. Is this inside or something?
in the back, what do you see?
See a lot of blocks.
A lot of blocks. There's a hint here. What do you see? You see something different from a woman?
Well, but if you squint.
Not you.
Sorry.
Yeah. Abraham Lincoln. Very good. Now notice Dolly gives you a cue by putting this picture of England here. Now there's a wonderful story behind this painting. In the early 70s, there was a big move at Bell Laboratories. They were anticipating video phones back in the 50s. And they were actually studying how much, right? So there they knew that they had to compress the data as much as they possibly could to get it over a wire and ship it. Data compression was everything. And so they were running experiments with humans, seeing about the best way to compress data. And there was a famous paper that was published in Science where they did a bunch of block, different pixel sizes for a picture of Abe Lincoln. And I guess Dolly sees this and says, hey, wait a second, I've done this before. And so he puts in the picture of Lincoln. And so did you see this one at the museum?
It's huge, and they put it like in like a huge wall. So you
Yeah,
can see
it's huge. Perfect. The guy who was doing the tour when I went through this said that one day this woman who modeled for this painting actually came through and said, "That's me." Well, I'm not going to comment any further on that. Now, if we blur it, seeing Lincoln is much, much easier. So tough here, but if we blur it, it comes from Lincoln. So basically what Dolly's saying is, hey, Bell Labs, you're doing all this research. I did this 30 years ago, and he did 2 versions of this painting, actually, but I love this painting. Here's one I found at airport in Paris. What do you see?
A bunch of women.
Bunch of women
Different positions.
in a very odd configuration. Can you see anything else?
Yeah, now I can. The profile of a man's face.
Remember, I saw this in Paris.
Yeah.
So is that a French nose or what? Right. I guarantee you would never see a postcard like this in an American train station. Paris, no big deal. All right, I'll show you one more just as a send-off to get us started for next time. This is another kind of double image, but it's double image for a different reason. Let's pick on you. Tell me what you see here.
I see a series of statues fading off towards the left.
And do you recognize that particular statue?
Seems familiar, but
Anybody recognize this statue? It's one of the most famous statues in all of the history of sculpture.
Statue of Liberty?
I'm sorry?
Statue of Liberty, maybe?
Not the Statue of Liberty. She's got no arms,
yeah.
hunched over. It's the Venus de Milo. All right, Ollie's famous for this stuff where he embeds things that he's copying inside his painting. So in this case, he's got the Venus de Milo in there. Do you see this thing down here? Anybody recognize that? All right, so he's got the Venus de Milo in there. Again, one of the most famous sculptures in history. And so she's plastered all around. And he's got this thing. Anybody recognize the figure in here? How many of you have seen this figure before? All right, how many haven't seen it? All right, you've seen it before? What is this?
The dog. Like a Dalmatian.
How many of you can't see the dog? All right, I'm going to change your brain forever. This is the dog's ear. That's the snout. This is his front leg. That's his hind leg. Can you get the dog to pop out? And once you get it, you'll never see this thing a different way again. Again, very famous figure looking at camouflage and perceptual organization that is embedded in this painting, where Dali is trying to get at the underlying perceptual principles that he's playing on here. Now, somebody tell me the title of this painting. What's the title? The Hallucinogenic Toreador. Do you all know, does everybody know what a Toreador is? Don't know what a Toreador is. Toreador is a bullfighter. All right, and how do bullfighters get dressed up? They have these big elaborate hats and these colorful costumes. Now that would suggest perhaps that maybe there's a Toreador in this painting, or 2 or 3 or 4 or 5 or 10 or 20. I think they're 13. I've never been able to see that many, but. All right, let's go through it. So this is the Venus de Milo, right? And so what do you see this feature right here as? Is that her breast? Okay, well, it's not a breast. Imagine it's a nose. Breast, nose, they have similar shapes. All right? And this thing here, you see there's something on her belly, that's a mouth. And this is not her head, it's an eye. And this is the hat, elaborate hat of the Toreador. And then the tie. And the colorful cape. How many of you can see the Toreador? So now he's getting this juxtaposition between the Venus de Milo and the Toreador, and there are several of them. So there's one here, there's a different one over here. I was told by the one time when I did a tour of this that there are 13 Toreadors in here. I've never found more than 3, but I guess if you study this all the time. Now, this is a different kind of double image. This is not painting images at different spatial frequencies. It's getting the visual system to confuse what's called figure and ground. And I'll end here, and this will be the setup for next time, when I'll show you a whole bunch of other kinds of Dali images. Yeah?
Is the head and the top left mean anything?
Oh, this head up here?
Yeah.
Yeah, you'll see this in a lot of Dali's paintings. He had his, I don't think they were ever actually married. The woman he lived with for most of his life was named Gala. And Gala, he often puts in his paintings, and I believe that's her. But if you look this up on the web, I'm sure you'll find pages and pages of discussion about this painting, and it might be able to answer that. I'm not 100% sure this is Gala. That's a guess. Any other questions before I let you go? All right then. Well, hopefully I've convinced you that now you're experts in Fourier analysis, and you're convinced that that's what the brain is really doing in early levels of the cortex. And so next time, we're going to switch gears and talk about perceptual organization and attention. So I'll see you next week.